All right, well, thank you for the introduction and thank you for the opportunity, Dario, to do this presentation. As you mentioned, this is more of a sharing of things that we've learned over the years on testing this gummy bear, goo, shmoo, whatever name you want to call it. So here's some things that we've learned on. I'm kind of going to take you from cradle to grave here on what we've learned on this gummy bear. So let me first share with you here. I guess I'm in the presentation mode, but it's not doing anything. Let's see. Oh yeah, so here's our famous gummy bear. You know, this little gummy bear is basically evaluated based on firmness, strength, and hardness. Unfortunately, we're not going to talk about this little guy. We're going to talk about this guy. So here, I felt that it was best to go ahead and start from the very beginning as to maybe what causes the formation of these gummy bears or this goo material. So we're going to focus on the anionic side of this chart. So we're going to look at this acrylamide, and this acrylamide is one of the monomers that goes into making an FR. The other monomer could be an acrylate, it could be amps, and those would be the copolymers. And then we would have what are now coming out to be terpolymers, which is a combination of all three monomers. But what we want to focus on is that the acrylate is a very strong anionic charge. The amps is an anionic charge as well, but it's a little bulkier. And then I want to look at these functional groups. We want to take a focus here on this amide and on this sulfonated group here on the amps. We're going to need those as references to identify the species whenever we look at the material that's actually flowing back. So what causes a gummy bear? So here's the hypothesis. We think we know what causes a gummy bear. And I think as we go through the presentation, there's going to be more and more evidence as to what the main basic element is actually causing this problem. So what we've done here is we've kind of taken everything in a little bit of a time lapse for you so that we have, I'll stop it right here. I'll try to stop it. So what we've done here is we have a cationic FR mixed at 2 gallons per thousand. All of these are mixed at 2 gallons per thousand, and they're roughly 30% active FRs. So we have a cationic, we have a copolymer acrylate, we have a terpolymer, and then we have another copolymer acrylate base. So as we're going through this time lapse, what I've just done here is after hydrating the polymer, we've added a 50 parts per million iron chloride. This iron chloride is simulating the iron that the FR comes in contact with to start the causing of the gummy bear. So 50 parts per million, the reason we use 50 parts per million is simply because as we've gone through time and we've tested various concentrations of iron chloride, as you know, iron chloride is very acidic. So it's a very strong acid. So what happens if you go much beyond a 50 parts per million concentration, what's going to happen is you start dropping the pH of your fluid. Then if you drop the pH of your fluid too much, as we know, anionic FRs don't like low pH. Cationics don't have a problem with low pH. Anionics do not like low pH. So once you start going too far below the pH of 5, then you start having other physical problems with the hydration of the polymer, and you don't get the full effect of the test itself. So by adding a 50 parts per million, we felt that that's a fairly good concentration to start with in determining whether this material, how it's going to react with coming in contact with a ferric iron, an Fe3. So we'll continue to go through this time lapse. So I'm going to take you through about 18 hours, 19 hours of test, but we're going to go through it fairly quickly. We're not going to go ahead and spend a whole 10 minutes or so going through the video here. So what we're starting to see very quickly in the first 14, 15 minutes, we're starting to see the agglomeration of this acrylate. We're not seeing much on the, and this is the beauty about the amps, in that you're going to precipitate an amps either way, but they're not going to agglomerate like the acrylates simply agglomerate. You can see very quickly that in a matter of 30 minutes, we've already started to develop this agglomeration of polymer. So let's go through a little bit of a time span here and take it through an eight-hour period, at which point we basically shut the test at 8 hours. So after 8 hours, you can see that this acrylate has already agglomerated completely out of solution. So basically we have a nice clear fluid simply because all the polymer has basically fallen out and agglomerated down here in the bottom. What you're seeing over here in this other copolymer is done basically the same thing. And what you're seeing here is just the heating effect. It's basically creating a little bit of a convection current, a little eddy current here as the water is continuously heating up, and the polymer that's already agglomerated at the bottom is actually just floating around. But again, this copolymer has also agglomerated. Now, as I mentioned, this cationic, because it is a positively charged polymer, coming in contact with a positively charged ferric, a ferric iron, is not really doing anything. It basically keeps all iron in suspension. The same thing here, in that what you've seen here in this terpolymer is you've seen probably some agglomeration, but very small amount of agglomeration taking place with the acrylate part of the terpolymer, but the amps is keeping it from actually agglomerating. What's happened is that this ferric iron has attached to the polymer, but it doesn't allow it to agglomerate. It basically allows it to basically stay in solution. So as we go over a 24-hour period, what we end up with is severe gummy bears for some, and of course we know that the cationic system is going to stay okay. But all the other polymers have basically fallen out, where this one would probably pass okay. It didn't agglomerate. It didn't create this glob of gummy bear that was formed on these other two copolymers. So that's one of the basic tests that we go through whenever we do any iron stress test. This is actually what we call the iron stress test. So this is where we think we start off with the creation of the gummy bear. So as we go further into the presentation, I think we're going to be able to back this up a little bit more as to, yes, I think we're right, but I think there's additional things taking place that also cause the firmness of this gummy bear to happen. So for those of you that are in the production side of the business, this is what you basically end up on your surface equipment. You end up with this material that we're calling gummy bear goo. It is a byproduct of what we think unbroken gel, unbroken polymer that comes back. It comes in contact with some of this ferric iron, and it creates these cross-linked solid material. So it can happen into your production facility where it comes into the screen, and here's what is actually, in some cases, actually flows back. So it is a nice, rigid, cross-link type material that is actually coming back. So we get some of these samples and we try to evaluate, is it really the polymer? What exactly is the composition of some of this gummy bear? And this is where we're going next, is let's break this little guy down and figure out what is the composition, what's it composed of, and how do we remediate it? And how do we keep it from happening? So I kind of put the test procedure here on what makes this thing up. We're going to evaluate two very basic samples that have come in here that came from the same well. And I think it's important to just kind of go step by step and kind of evaluate what are the steps in getting this done so that we can identify what the composition of the gummy bear is. So the goo observed in the flow back is basically something that comes back after the hydraulic fracture. And it's a combination of unbroken gel for one, and we know that. And, you know, I think it's simply due, it happens predominantly in a low bottom hole temperature well. After the frac, we've cooled the formation down significantly, even though we add a ammonium persulfate, or some temperature, some breaker to help break the polymer at 140 degrees, for example, or 150 degrees. After you pump millions of gallons of cold water through the formation, your cool down effect is going to be so significant that these breakers don't really kick in. They don't activate until you reach bottom hole temperatures of about 120 degrees F. So without the breaker, the oxidizer actually kicking in to help break some of the polymer backbone, we basically have unbroken polymer. So if we were to do a cool down or a heat up type program in a low bottom hole temperature well after pumping millions of gallons of fluid, we would probably see that it probably takes several days to get back to 140 degrees, or at least to 130 degrees where the breaker can actually kick in. But by then it may be too late. It may have already come in contact with the ferric iron, and it may have caused some of this agglomeration, which makes it a little more difficult for the oxidizer to break. Because over time, as it commingles with your hydrocarbons and your organics, then you're consuming your oxidizer, and it may not be, it may not have the availability or the amount of oxidizer to actually kick in and work on that polymer backbone. So where does this Fe3 come from? It could come from a lot of places. One and foremost, if you have iron, Fe2 in the water, iron that is the ferrous iron that is actually in solution, and we're pumping oxygenated water, it's quite possible that some of this may come in contact with the Fe2 to form Fe3. But I think a lot of this is actually coming from something we're putting in ourselves, and that's the acid ahead of the frac. If we're spearheading with acid, that could possibly be one of the main bases for the creation of the gummy bear, and maybe the creation of, we're introducing the Fe3 right into the immediate wellbore. So what I mean by that, and I'll explain it here a little bit, but there's also the solids that actually come from the formation itself. The formation finds the turbidity of the actual sand. There's a lot of other solids that can be introduced into the well that may help make this body a little more rigid. And then we have all these divalent elements in the water, the barium, the calcium, the strontium, magnesium. These divalent elements also contribute to the formation of the gummy bear. And then of course we have our good buddy, the hydrocarbon himself, who's going to come in contact and help create a little bit of an emulsion, which tightens that gummy bear just a little bit tighter. So when we talk about the spearhead acid, you know, there was another operator who actually did some work where they ran the spearhead acid, and then afterwards they went ahead and caught water samples of all the fluid that is actually coming back and how it's coming back, and that as they were captured, they were measuring the amount of iron as early on right after the frac, and then progressing over a period of time. So what happens is we always think that a spearhead goes ahead of the frac, it gets pushed further out into the fracture, and we never see it again. Well, that's not exactly what's happening. What's happening is that some of this acid and this residual iron that comes from the casing, it comes from the pipe, it comes in contact with the formation itself. If you have any pyrite, that acidizing and the chloride clay that comes in contact with that acid is releasing iron. So what's happening is this acid is residing right at the immediate wellbore into the matrix of the rock, right close to the wellbore. So when you bring the well back, all that iron is just sitting right at the immediate wellbore, ready to see that unbroken polymer, and it's already starting to fester as an agglomerated polyacrylamide. So here are the two samples that we actually tested for example purposes. So what we do here from left to right is, of course, this is the gummy bear. And this particular was an ideal gummy bear in that we could actually take it into your hand and it feels like a piece of rubber. You can stretch it, you can pull it, and it won't tear apart. It is so rigid and so tight of an emulsion and so tight of a cross-link system that it doesn't come apart. You can't pull it apart. There's sometimes we get what we call gummy bears come back, and these polymers are not cross-linked. You can actually pull them apart. They just agglomerated in a point to where they're not fully cross-linked. So in this particular case, we're looking at an example where we actually see a very rubbery type material that's very difficult to break. And this is the gummy bear under the microscope, and you can see how wet it is. And of course, this material is got water. It's already hydrated. You can see some of the redness, which means that there is iron present here. So again, after what we typically do is try to figure out, one, how much water does it actually have? So here we have an example where we go, when it goes from an actual sample, an aliquot of the main sample, we dry it. This contained approximately 50% water. So it is fully hydrated. It's about 50% fluid. So just to help understand another example here of a time-lapse video of what goes on in various types of solutions. So what I've done here is we put a DI water by itself, a toluene, of course, is a solvent to help remove any of the hydrocarbons that may be present around the sample itself. A 15% hydrochloric acid, and a lot of people like to remediate with 15% hydrochloric acid. So acetic acid, which is the glacial acetic. This is a 10% glacial acetic. And then I didn't label these because these are surfactants in the water, the acid, and the acetic acid to see if it would help do anything different than what the actual baseline did. And then we have 10% citric acid and IPA. IPA is isopropyl alcohol, kind of a non-polar fluid here. So we have water, which is polar, and IPA, which is non-polar. So we're going to take this through a 24-hour period just to give you an example as to the solubility of the gummy bear. Now, each one of these gummy bears is approximately 1 gram sample in a 40 ml sample of fluid. So let's take it through the first few hours. Now let me grab it first. So here's 4 hours. So what do we see in the first 4 hours? We look at the DI water. After 4 hours, the DI water, basically what it's done to the polymer is it's starting to hydrate the polymer. So let's focus on the DI water first. Over the DI water, over a 12-hour period, you can actually see the hydration of the polymer itself. If you look at the toluene, it hasn't really done anything with toluene. It's basically just sitting there, and you would expect that unless there was a tremendous amount of oil that is actually putting this thing together. There doesn't appear to be a whole lot of oil holding this together, so it's not really doing anything. There may be a sheen up here of oil, but from the gummy bear breaking down perspective, it's not doing anything. Acetic acid and HCl are not doing anything. If we look at the 10% citric acid, you can see that the citric acid is starting to do something. It is actually starting to break down the actual gummy bear. So what we think is happening here is that because citric acid is a very good chelator of iron, that it may be actually pulling out some of that iron, destabilizing the polymer, allowing the fluid to actually, the low pH fluid to break down. So remember that hydrochloric acid has a pH of less than 1, 0. And then we have acetic acid, which has a pH of roughly 2, and citric acid, which has a pH of about 2 or 3. So as we go through time, all we end up with is a better hydrated polymer. This DI with a little bit of surfactant did actually enable it to hydrate a little bit faster. Simply what's happening here is the surfactant is actually helping pull some of this oil, allowing the fluid to actually come onto the polymer and fully hydrating the polymer. But look at what's happening over here on the 10% citric acid. The citric acid has actually pulled the polymer apart. And so now all we have is solids of something that was held together that now can very easily be produced out of the well. The IPA didn't do anything as well. It just basically just sat there. So over a 22-hour period, we basically have a gummy bear that was untouched, no solubility whatsoever, with the exception of the 10% citric acid. Everything held together pretty nicely over a 24-hour period. So now let's look at the fluid breakdown of this thing. So this is important data. Now we're able to come back into this 40 mils of water and do a water analysis and determine, hey, what elements actually came apart here? So for starters, let me start off over here with the 10% citric acid because that did so well. So the 10% citric acid was made with a 10% by weight citric acid. So 90 grams of water, 10 grams of citric acid to form the actual 10%. It was done with DI water, so we were not introducing any elements into the actual test itself. So the test results that come out are basically from the actual sample itself. So for hydrochloric acid, even though it appeared it did absolutely nothing to the solids, the salts appear to have come out, which stands to reason, because sometimes when you look at these samples and you're going to hydrochloric acid, they seem to get really tighter. They shrink in size, but they get tighter and firmer. And that could be simply because we're pulling all the salts out. And here's pretty good evidence that the salts actually all came out. So we had the barium, calcium, iron. Now remember, when you look at these iron contents, this iron is 35 parts per million in a 40 mil solution out of a 1 gram sample that had 40% water. So the iron content is pretty high. Even though it shows like 35 parts per million is not much, that 35 parts per million is what's in 40 mils now. What was it in a half a mil of fluid? The potassium, and we're talking about the divalents here, the magnesium, manganese, not much manganese, sodium content, strontium. The one thing that I found interesting out of all of this is that the one element that actually came out pretty consistently over time is this aluminum. And aluminum, as we know, a good partial transitional metal, is a very good crosslinker as well. So is this also a contributor to causing the firmness of the gummy bear or not? There's still a lot of work that needs to be done here. These are some early results on some things that we've learned over time. I mean, we're not a research lab, we're a testing lab. Our job is to basically take the information or take the material and help you analyze it and tell you what it's made of. Now, this column over here to the far right is that we actually took this sample, another gram of this particular material, and fully digested it. We added temperature, we added time and temperature to fully pull everything we could out and dissolve everything in the sample itself. So what we ended up coming out with when this 1 gram material was 77,000. So basically what's ironic is that if you take this information here, multiply by 10, you almost come up with these numbers on this other side. But look at the iron content. So we look at iron, we're 263 parts per million of iron in that sample itself. So Fe3 is definitely, or iron is definitely a culprit in helping this thing come together. The aluminum content that came 41 parts per million. Now, aluminum, for you mineralogists, you know that a lot of the clays, part of the clay composition is aluminum. So could the aluminum be coming from that? It's the acidizing portion of it could be affecting maybe some of the mineralogy, causing some of this aluminum to solubilize and helping in some of the cross-linking material, as well as some of the solids that and fines that you basically generate over time. So we take this sample and we start breaking it down and start to evaluate the actual material. As we start to separate this material, we're able to identify or help identify what the composition is. So here we basically have, we know it's swelling. And as we're looking at the sample, you can see that this sample has even got enough polymer in it to make it lip, almost like a cross-linked fluid would actually lip. So we know that there's polymer present here. So we take it to the next phase in trying to identify this. So we use, in phase 1, we use what is the FTIR, the Fourier Transform Infrared Spectroscopy. So in here, I basically, I added another piece of information, and then we also do zeta potential, just to give you an example of those 4 initial FRs that we tested, which are these right here. These are the 4 initial FRs that we actually looked at. We looked at the cationic, we looked at the copolymer, we looked at the terpolymer, and then we looked at the copolymer in sample D. So I basically took the zeta potential, which is actually measuring the overall charge of that particular polymer, and you can see that the cationic, which is sample A, had a zeta potential of 72 positive. The anionic copolymer, the first one, had almost 90, negative 90. The terpolymer had negative 81, and the one that agglomerated very, very easily had a zeta potential of 100, negative 102. But to help us identify, we use this FTIR to help identify the functional groups. Remember, we looked at this structure early on. But what we're looking for predominantly is this amide structure. This amide structure is what the FTIR is. It likes to look at these bonds. So it's going to look at the carbonyl bond, for example. These carbonyls are this C double bond O. And then we look at the CNs, the NHs. So this spectrometer is actually, it goes through its infrared signal, and it converts some of these signals into some of these how it identifies the bond in the molecule itself. So these bonds are going to occur in certain parts of the wave number. So what it does is it takes a wavelength of IR and the inversion of the wavelength converts it to a wave number. And this wave number correlates to a specific point on that wave number of a specific type of bond. So we would look for your NH2s. Your NH2s would reside in this part of the spectrum. Your CH, the thing about CH is that anything could be a CH. You know, all your hydrocarbons are going to be CH. So everything's going to have CH, and you have a lot of CH in here. So we look at that as well, but it's important to look at the NH and then to look at this carbonyl group. This carbonyl group is this part of the amide structure to actually identify whether it's a polyacrylamide or not. We have the CNs, and of course, on the sulfonated AMPS one, the AMPS will have this sulfonated group over here. And this sulfonated group we can identify depending on where it is. So remember that the green one was a sulfonated one. So we're looking for this particular peak here that doesn't exist in any of the other three. So again, whenever we have one of these gummy bears actually show up in the lab, it's important to also have, if possible, an actual sample of the FR that was actually used on that particular well. It's truly important. It's very important to have that actual FR sample so that we can use it as a reference whenever we do the FTIR. So we take the sample as is, and this is the blue line, and the water also resides over here. So whenever you see a reduction here in this particular peak, that means we dehydrated and pulled the water off. So again, we're looking at these good functional groups to try to help identify what this particular product may be, or what this flowback material may be. So we do have an FR reference. So the sample that was actually dried, we compare it to that FR reference, and we try to identify these functional groups to determine whether it's FR. And in this particular case, it was a very good match. Now, sometimes iron will have a tendency, because it's looking for specific bonds, iron will have a tendency to maybe shift some of the curve. So there is some curve shifting taking place here. Now, I am definitely by no means an FTIR expert, and there's so much to learn on just this one instrument alone. But what has been consistent is whenever we see an iron crossing material, we sometimes see this shifting of the curve. And remember, there's a lot of other things. You're never going to get a perfect match simply because there are other things that's in the gummy bear itself. You're looking at a baseline reference, which is a pure reference material, versus something that may have already reacted with something else. So you're looking at a baseline versus a reacted material. Now, there was hydrocarbon here, so we compared it to a wax. What we do see is, remember, we looked at those CH groups. So it's definitely has, we know it's not a wax, but it's definitely a hydrocarbon residual that was attached to this particular sample. So for this first sample, what we basically have here is the composition that is, say, 50% water, 50% solids. Tried to identify what those solids were. We know that it's predominantly polyacrylamide with a tremendous amount of iron, calcium, sodium, a lot of salts, and 41 parts per million of aluminum-3. High sulfur, all of these are, of course, very strong divalence elements. Now, for the second sample, I'm not going to take you through all of this in the detail that we took sample 1, because a lot of this is repetitive, where we take the sample and actually go through its go through its solubility phases, go through its dehydration phases. So here, what we're doing here is we have solids that actually came out. Now, on solids, some people like to use the FTIR for interpreting types of solids. I like to use the X-ray diffraction. XRD is, for me, one of the better instruments in identifying crystalline material. Now, XRD does not identify, is not very good at identifying amorphous material, but it's an excellent tool in identifying crystalline material. So after washing it and removing some of these fines, again, the sample through an FTIR as is versus dried, we do see some polyacrylamide, but not as much. Here we're comparing it to a sand and this is some of the references you can use on the FTIR, is comparing a sand. So there is obviously sand based on the peak that's right here to help it identify as to whether it is. And it does have oil, but the XRD, what the XRD is able to help us identify is that in this particular case, this sample was 76 or 77% quartz, K-spars. So total sand, total silicate was 88.4% silicate, 10% carbonate, and 1.3% clay. So in this particular case, this was more dominant on the solids as it was on the polymer. There was polymer, but more solids in this particular sample than the first sample. So breaking it down, we had a tremendous amount of calcium, which is probably the calcium, some of the calcium scale and some of the carbonate that was actually present in the sample. A tremendous amount of iron, 2,700 parts per million of iron. Again, the iron helping it hold together, 85 parts per million of aluminum. Everything else was very similar to the first sample. So let's talk in the next 5 minutes. How do we get rid of this stuff? Well, we've already saw early on that 15% hydrochloric acid really wasn't doing much. And so the only thing that seemed to be doing anything was the citric acid. So another little video to help demonstrate the difference between this and this is 15% hydrochloric. And so GB is the gummy bear. This is the weight of the sample itself, 1.1 grams, 0.9 grams, 0.9, 1.0 grams of the actual solid. Again, these have a surfactant. I wanted to see what the effect of a surfactant, of a good surfactant, oil removing type surfactant would do to the actual gummy bear. So over a time period here of 8 hours, what's happening is that the 15% hydrochloric acid, even though it's in a dynamic, the first test was in a static mode. This one is more in a dynamic mode. Even though it's in a dynamic mode, the only thing that 15% hydrochloric acid is doing is basically dehydrating it and just taking the sample and just bouncing it away. So what I wanted to show here is you can start to see the oil coming off of the sample. Now with the surfactant, with a dispersing surfactant, what's going to happen here is it's going to pull the oil out, and it's going to pull the oil out a little faster. So it enables the citric acid to actually go in and actually help break down some of that polymer. So at 1%, it seemed to be the optimum. So what we're looking here from the top is the oil sheen that you see here, that is just basically parked itself around the rim of the beaker versus one that is actually dispersed across the entire fluid. So as we go through a 24-hour period, we're able to basically say the citric acid in this particular sample worked very well in dispersing the polymer back into some solution to help remove it from your wellbore. Now, the beauty about citric acid versus the hydrochloric acid is if you were to run hydrochloric or acetic acid, those are a little stronger. Although the strongest is the hydrochloric acid, you're going to release more fines. So if you have a carbonate formation, what you're going to do is actually release a tremendous amount of fines and create a little bit more of a problem, because now your gummy bear hasn't gone away, it's dehydrated, and you're adding more additional fines to it. So you might possibly even plug up the well. Where the citric acid is a very mild organic acid. This mild organic acid is going to react very slowly on your formation, shut the well in overnight, and over a 12-hour period, your gummy bear is in essence gone. The surfactant helps it speed up a little bit. The surfactant is helping it get to the gummy, allowing the acid or the citric acid to work and separate that gummy bear. Now, it's not dissolving 100% of the gummy bear. There's a lot of gummy bears still in solution. There's still a lot of suspended solids in here, but enough to allow it to flow out of the well. Again, breaking it down, what's in the actual fluid itself. In the fluid itself, we find very similar results for samples A, B, C. And the only reason your phosphorus is high is because I think this surfactant has a phosphate ester incorporated into the surfactant package. Then that's what kicked up the phosphorus in this particular case. But you can see that the iron content is still there. It is a composition of iron that's holding it together, along with a lot of these other elements and some of the solids that actually, and the oil that actually help emulsify this material and keep this gummy bear together. Now, it's important to understand that this was, for all the analysis that was done was for this particular sample. If you have a sample, it's important to go through this entire process to help identify the breakdown and not jump into conclusions and say, oh, I'm going to run citric acid each and every time. That in order to make sure that that's the right treatment or right remediation treatment for your application, it's important to have it tested. I thank you for your participation. I really thank you for your time, for everyone being here. I leave it open to any questions, Dario.
All right, thanks a lot, Frank. I thought that was a very interesting presentation. So I want to go back to the cationic versus anionic. You said the cationic with the iron chloride won't form these gummy bears. Is that correct?
Correct.
So isn't the simple solution, or what I'm getting at, prevention is much better than the cure. We'd rather prevent it. So wouldn't the switch from anionic to cationic be simpler?
Oh man, I tell you what. Let's open up Pandora's box here. So
Yes, let's do it.
So here's the deal with cationic systems. Cationic systems are good. They have their applications, and the Northeast runs a tremendous amount of cationic FRs. In some cases, a cationic will stay cationic for a period of time, and then it will actually convert over to anionic. So depending on the FR type, I'm not saying they all do. I'm saying the ones that we've seen, some of the ones we've seen, you have to worry about that to make sure that it doesn't go from a cat to an anionic, and then you run stage two. Stage one has already gone into an anionic mode, and you have communication between a cationic and anionic FR. Now you've got yourself another problem, but it doesn't always happen. Brine materials, you typically run cationic systems in a high brine scenario. So that's why they run them in the Northeast, is simply because your TDS levels are going to be 250,000 plus. They run them in the Bakken, they run them in the Northeast. But down here where your waters are a little fresher, you do have that worry about it converting to an anionic. And I think they're a little more, I don't know about the cost, the economics. I'm going to stay out of the economic equation.
Yeah.
That's not my deal. I don't deal with costs on FRs, so don't know the answer to that. But the reason that likes, well, it's cationic already, so ferric acid being plus charge, they're not gonna cross-link.
Okay. So following on to that from Michael Lance, he says, Frank, good work. Have you found an optimal level of amps to prevent formation of the gummy bears, I assume? Where do you think AI is coming from? Oh, the aluminum, sorry, is coming from. We have seen one gummy that likely formed from clay, which had aluminum in it. Did you test other iron chelators? We found other chelators at much lower dose rates worked well.
Yeah.
So and Carl talks about, have you used things like EDTA or erythorbic acid?
No, I mean, the cheapest thing on the planet, citric acid. But again, this was just a experimentation. Yeah, there's a lot of work that needs to be done, and I'm sure very similar to what Mike is basically saying there is the citric acid appears to be that chelating, that sequestrating. It's pulling the iron out of that gummy bear, destabilizing it. So a chelator of some sort would work almost, you would assume that it would work under the same premise. That it would have that same effect and try to pull that iron out, destabilize the gummy. But again, all these things need to be tested. They may work. The premise is the same.
Okay. Can you talk about the surfactant you used? What's the nature of it? I don't think we want to talk about commercial names, but what type of surfactant was used?
I mean, this is a unique surfactant that was given to me. If you want, I can give you the contact information on that surfactant if you send me an email or something. But like you said, I really don't want to introduce anybody at this time. But yeah, it's a surfactant that basically helps remove oil. So it's almost like a demulsifier.
So with that, then all your testing is done with agitation for a period of a day. Can you talk about not, because once you pump in the formation, you're going to shut in. There is no agitation per se. There might be some slight movement early on, but that's it. Would you recommend a longer soak period then?
I think as you saw in some of the presentations, over an 8-hour period, you're pretty well done. But and this was at very, very low temperatures. So if you add more temperature to it, I would say that it would offset for the little bit of stirring that I did. And I'm not going to say that we're not seeing any dynamics going on downhole. I think there's still dynamics taking place downhole, even after you shut the well in, just simply from the commingling of fluids, the changing of high salt concentrations versus low salt concentrations. I think there's always dynamics downhole taking place. I don't think it's ever, with the exception of what's in the wellbore itself, in a static mode.
Okay. So kind of following with how these things are formed, Barry Dean asks, what role, if any, do isolation plug drill out fluids play? Compositions include PAM FRs, pipe on pipe friction reducers.
Are you talking about
so you've pumped all your fracs, now you're going in with a clean out, you're milling out your plugs, and you're using various fluids in that. Would that add to the formation of these?
during the drill out phase?
Yeah.
So, I mean, that's a good question. I think it's important to make sure that your fluids are definitely compatible. I mean, you kind of have to look at it from a holistic perspective, from cradle to grave until the well is put on production. But what you're hoping is that your bottom hole supercharged. You just got through with the frac, so your formation is supercharged. So you're hoping that the bottom hole pressure is going to keep that invasion to a bare minimum. And hopefully it's not going the opposite direction whenever you're drilling out, where your hydrostatic head is exceeding your bottom hole pressure and you're actually leaking fluid back into the fracture itself. If that's the case, then yeah, you're absolutely going to cause an additional problem if you don't have the right polyacrylamide.
Okay. So Leopoldo Sierra has a couple of questions. It says, Frank, nice to see you again after a long time. 2 short questions. 1, based on the structure of the gummy bear material, do you agree that they are formed inside the wellbore and not really inside the fracture or rock? I think it's impossible for these low permeability unconventional reservoirs to flow back this material.
Yeah, I think that's the question that's still out there, and I kind of understand where he's coming from, because I kind of think the same way. It's how, if it was in the actual reservoir itself, it would be difficult to pump it out of there. But it's got to reside. And we talked about this acidizing early on, where the acid is residing at the immediate wellbore matrix of the rock. So what's there, I think, is pretty much what where the gummy bear is actually residing, right at the immediate wellbore, where the supercharged pressure is going to allow it to actually push it out of the wellbore.
Okay.
Again, that's a pure guess, because I've never actually seen downhole enough or understood downhole enough. I mean, some of these things come in blurb in little blobs. You produce it for a while and then it stops, and then you produce it a little bit more and it stops. And I don't know whether this thing is occurring as your bottom hole pressure is changing along the lateral of the well. I don't know. I think that's more for the reservoir engineers and production engineers to get together and figure out how far back into the reservoir is this thing really at.
So I guess I never really thought about it that way, because usually production facilities are the ones that complain when they're getting these gummy bears, emulsions, stuff that they can't handle. But from a production standpoint, if it's being formed in the wellbore on production, you'd think that productivity overall wouldn't be impacted. Do you have any comments on that?
Well, productivity is impacted. How many remediations do they go back into? I mean, I know a lot of people that do a tremendous amount of remediation work, which means that they're able to get the production back very similar to what they had. So this stuff is actually a long-term thing. I don't think it's a short-term thing.
So that kind of feeds to it forming somewhere in the in the formation as well. Because if your remediation is cleaning it up and your productivity is increasing, it's not from just a wellbore cleanup.
Right.
Okay. All right. Let's see. How would breakers and natural processes change the nature of a cationic friction reducer from Hap Pinkerton?
How would a oxidizer change a cationic system?
Hmm.
I mean, all oxidizers are going to break the backbone of a polyacrylamide to some point. They're going to accelerate it. They will naturally break to a certain level of backbone, but remember that the polyacrylamide is a very big molecule. So as it breaks down this backbone, all the oxidizer does is it allows it to break faster if you're in that range where you activate the oxidizer. If you're not in the temperature range to activate the oxidizer, you're going to have to wait until it actually gets to that temperature range. Now, assuming an oxidizer is going to be very reactive to anything it wants to see, or if it sees hydrocarbons, it's going to react on hydrocarbons as well. So sometimes the oxidizer will get consumed and it doesn't really have an opportunity to work on the polyacrylamide itself.
Okay. Clayton Smith says, great presentation, Frank. Thanks for putting this together. My question is, how would you explain the fact that even though the HCl did not dissolve the gummy bear well, the fluid analysis showed that the iron content was almost the same as what was shown in the citric acid solution?
I asked that same question to Frank Zamora as well. Why and how? And it didn't do anything else. I don't know the answer. That was a very puzzling find as well, that it pulled out that much iron, but it did not break it apart.
Okay. Let's see. Randy Serrett. Nice presentation, Frank. In the polymer flooding business, we see this problem whenever HPAM contacts a hot surface, heat exchanger, ESP, jet pump, etc., and divalent cations. We don't have any acid. Our conclusion is that the calcium or magnesium is normally the key to gum formation after the HPAM goes to 80 degrees plus of hydrolysis. Is it possible that the calcium or magnesium is really key to gum formation? Do you have any heat source in your application that might drive HPAM to a high degree of hydrolysis?
Yeah, I think they're contributors, absolutely. I think all these divalents are contributors. Um, so, you know,
Okay.
again, it's one of these situations that we very quickly in the industry jump to iron as the primary culprit. But we've never been able to simulate it in the lab. And until we get to the point that we can simulate a creation of a gummy bear in the lab, then we can say, absolutely, these are the constituents that come together that's going to create this blob of gummy bear.
So how much of a problem is this? How often do you get samples in the lab that you test?
We get quite a few of them.
Okay.
Quite a
And
few
is
of them on new wells and old wells.
and it's difficult to replicate.
It is very difficult to replicate. Simply
Okay.
because it's a combination of fines, oil,
Just the right conditions, I guess.
at the right conditions.
Okay. Have you tried non-ionic FRs?
Yeah, and so everything's a give and take, there are non-ionics, but they haven't in the past performed as well on your friction reduction characteristics, so. They may work, they may not give you what you want from a performance perspective, especially when you're dealing with brines. So in high brine scenarios, you want to be able to, if you're in fresh water, they may work, I don't know. But most people in the industry use acrylic based.
All right, we're at 11 o'clock, so I'm not going to extend the session. Thank you so much. There's a few questions out there. Please reach out to Frank if you have more questions. Want to talk to him for your particular issues and cases. Frank, thank you so very much for your presentation today.
Yeah,
And
you bet. Thank you everybody for your time, and everybody have a great week.
awesome. So just a reminder for next week, Joseph Mihovich will be talking about Crosswell LFDAS for quantitative analysis and hydraulic fracturing diagnostics. And as always, if you have a case history, you have some technology you want to bring up, please reach out to us and we'll get you scheduled in for a presentation. It's what helps make these Wednesdays successful, is bringing good high technology and case histories to the public. So with that, thank you all, and we'll see you again next week, same time. Bye-bye.